Welcome everyone to today's video. Today I wanted to shortly talk about microkernels because I mentioned this already a couple of times in my videos before the last live streams, that I would ideally prefer a microkernel, and I thought I shortly give you some ideas about this. A microkernel and specifically welcome the Dense 34. No, you have not missed it, we just start. And so microkernel, there exist several of them. Many are not that known. One is GNU-hurt that apparently never gets finished, and another is QNX, for example. And there's also the huge L4 family of microkernels. And today I did not want to go in all the details of the implementation and everything. I only wanted to give you a little bit of an idea and also not install them or code too much. I just wanted to make some points because many people always point out microkernels are too slow. And yes, usually they are a little bit slower, but nowadays with today's high performance CPUs and in times of Intel CPU bugs that partially also affect other vendors, Spectre, Meltdown and all the friends in that security family. And I made some notes in today's flight that I wanted to show in a minute. But I also wanted to say, so one thing, when we already with security vulnerability mitigations for Spectre, Meltdown and such lose a lot of performance in the range of 5 or 10 to 50% or sometimes even more according to some benchmarks and articles. So with this security mitigations in Linux and other kernels, we lose a lot of performance anyway. And then I thought it's a good time to talk about microkernels again, because when we make things more secure, maybe we should make the whole architecture also nicer. So GNU-hurt is probably as old or older, similar old, something like that, as Linux. Many of you might have heard about this. Few have probably tried it out. It is not that developed. Maybe a handful of people, maybe the last years. And of course, a core team of 5 people is unfortunately not really that many people to finish a whole microkernel thing. And what is different, you see this here a little bit in this picture. The difference is that this is a multi-server microkernel system. Multi-server meaning that all the different parts of the kernel, for example, file system, graphic drivers and everything is running in separated processes. And this means that a graphic driver cannot crash the rest of the system. Or, for example, I wanted to live stream 30 minutes ago already, and this video for Linux USB UVC video driver also crashed in the middle of setting it up, and then I had to reboot. So, so much to that. But I also had already sound drivers, and probably every one of you had already something crashing, not only Linux, also macOS. Even macOS is based on Mach. And ironically, GNU-hurt is also based on Mach, is written also here, GNU-hurt and GNU-Mach. And ironically, macOS is also based on the Mach microkernel. However, macOS is not really making use of this as far as I've seen. So they have basically a microkernel for process management, and then most of the stuff is actually run in one huge BSD task. So they only mostly get the security penalty of a microkernel without many benefits. But that is their challenge, not ours. And why I want a microkernel is quite obvious, I hope. Let's change to this camera. I hope it is mostly readable. On today's flight back to Berlin, I made some notes, and yes, I could have scanned them, but then I could not have drawn around on this also while showing it to you. Let's focus this a little bit more. And because then it is also supposed to be more interactive if I can make notes in this. And basically everything of this notes, so what I've done here in 1 hour of flight time or 2 hours, I actually made notes what we would want to implement, because it already starts. Let's try to zoom in here. This is also why I could have tried to scan it and draw on the Microsoft Surface, but then I thought it is nicer to be able to draw on this. And it starts because the problem is I worked on, first of all, I was thinking about microkernels already for 20 years, not doing whole research, but I was always thinking they are architecturally preferably. And when I look on Grub2, I think I commented this on some YouTube video, and when you unpack Grub2, you get 50 megabyte of source code, which is of course enormous. Then I was shocked and I unpacked the Linux kernel. The Linux kernel in the meantime I think was approaching a gigabyte, which is also crazy. All those million lines of code. And mind you, everything is, so the Linux kernel is a monolithic kernel, meaning everything is running in this kernel space, in this kernel address space. So this means each driver can crash your system. And unfortunately, it sometimes happens, as I said, even on Windows and things like this. And also when you think about this, in your bootloader here, you have everything duplicated. So all the, or not everything, but a lot of things. So the bootloader also has code to read file systems, ext2, 3, 4, betterfs, xfs, jfs, maybe even ntfs, you name it. Some graphic stuff. So basically even the graphic stuff is implementing a little bit frame buffer kind of stuff and so on. And when you look on Grub2, how huge this project becomes, 50 megabyte is of course enormous. Wouldn't it be nice if you could share all of the stuff you implement in your bootloader also for your kernel? And not only this, even when you compare the Linux kernel, you have the huge amounts of code for file system, and then a lot of this is replicated again for user space tools to check the file system, for assembling write and data recovery, finding write volumes and such. So even in the Linux kernel, a lot of code is written twice, often cut and pasted, but that doesn't make it that much better, for user space tools doing administrative stuff. And even then, you have duplications. For example, the frame buffer in Linux is similar to, or of course not 100% similar, but to some degree similar to unaccelerated graphics in the Xorg driver for the frame buffer driver in Xorg. So even there on many levels you have a lot of code duplication, and I think this would also be nice to avoid. And of course I'm not that crazy, because one could think that I'm größenwahnsinnig, getting a little bit crazy and over my head here, but that for 20 years, you see, I'm not that crazy to start it immediately, although I started it a little bit. But for 20 years, I focused on other things because I am very well aware that it's very difficult to sell a completely new operating system. And not to mention that it may take 10 years or much more to get a halfway decent working system. Of course, if I would hire 50 people, and maybe I would have something halfway decent working in a year or two. But I only wanted to give an overview, and as I've not done it for the most part, you probably see that I'm not that crazy. However, I thought with all this Sound Blaster and S3 Verge and soon other stuff, PS3 RSX, which now I'm back in Berlin, as you can see here, so we will also continue with that. PS3 RSX not forgotten. And I wanted to point out something. So I made here some notes. Let me see what we can get here on screen besides somewhere. I'm not that satisfied with my focusing work here. Let's try to angle the camera a little bit different here and focus this again, because I wanted to give a brief overview what kind of stuff we need. And I was thinking, so So I do not go into all those details. So I've not written all this in machine code and was thinking this flight just in exactly how I want to implement IOCTLs and message passing and whatever. But to get this started, we do not need that much. Just some system calls or something for seek. Basically, you can wrap a lot of things in basic primitives like open, seek, read, write, and stuff like this. And basically, for the inter-process communication, so you have an application, and the application is performing IOCTLs like read, write, like in a regular kernel with Linux. But in Linux, everything is handled here in this kernel portion of this. And in this microkernel, in a real, not like macOS, but a real like Herd, but just maybe a little bit more modern or so, microkernel, you would have not the kernel handle this, but the kernel would pass this IOCTL, this message, or however you want to implement this, to some other process. And in my idea, all these processes like file server process and graphic, like we have in Linux an X server anyway, just that the X server is not doing that much work nowadays anymore. With 3D stuff, everything is passed down to the kernel driver. So in my idea, we would have a graphic server here, a network server, and you would also, if something crashes, then only the network server would crash or the graphic server, and you could restart it. Wouldn't it be amazing that the graphic server is completely isolated, and when your NVIDIA or Intel driver crashes, just the graphic server portion of your process stuff is started again. Of course, the user would still lose the window, the display content for a second or two, just like maybe in Windows where it sometimes works like this or so. But it would certainly be more amazing than with my video capture where I had a frozen Linux kernel 30 minutes ago when my